Hi all. So let us wait for some 5 minutes for others to join.
Okay, ma'am.
Yeah, okay. Hello, hello, hello. Okay, fine.
Yes, ma'am.
Yes, ma'am. Yes, Kurshid and KG Krishna sir only is here now because I have changed my timing for today's session only. So due to some issue. So let us start this session, and those who require they can see the video on this one recording. So I think in this week 6. The Aditya sir taught this one analog to digital conversion of signals and introduction to sampling. So I have covered this introduction to sampling and derivation of sampling in some uh, few lectures before. So I think I will again deal with it, and we will see the reconstruction part, and then we will move to the questions part. And Kushit, are you giving exam of this subject, NPTEL exam?
Yes, ma'am. Yes, ma'am.
Did you registered?
Yes, ma'am. I have registered already.
Okay, so how many marks you have got in assignments till yet?
Ma'am, in one assignment it was 90, in rest of them I've got 100.
You have
And
got
those,
100. Okay,
yes, ma'am.
okay. Nice, nice. So, sir, you have also registered for this exam. KG Krishna, sir? Yeah, I think sir has also registered for the exam. So it's okay. Like in last two
Yes,
live
yes,
sessions.
madam. I registered,
Yeah, yeah.
but just looking into because I don't look at my progress, so I just looking at it and let you know.
Okay, okay. Because this is very important for you. Like you have given previous exam for digital communication, I think. So in that exam, you might have observed that the questions are mostly related to assignments or some of for the modification of assignments. So
Yeah, yeah. Between 70 and 90, I got, madam. All previous assignments.
okay, nice, nice, nice. So yes, I think yeah. So assignments is very important, and then in the last like week 6 is going on now. So in last week 11 and week 12, I'll cover mostly this exam pattern questions, so that you will only have the exam idea and you can score most of the marks. So mostly in week 6, week 7, and week 8 and week 9. Up to then, I will cover almost all the week assignments questions, and then after that we will cover the practice questions so that you won't have any problem in that. So let us cover for this week, week 6. So here in this week, you have been observed that sir has taught analog to digital conversion of signals and introduction to sampling, because this is very important for the uh, filter perspective. Now, since analog to digital conversion requires sampling, because whatever we hear in nature is analog in nature, and due to which we have to convert to digital for better for better complexity reduction. Because in digital communication, you can have one modulation scheme, and you can use the same box for other modulation scheme as well. Because in PCM, if you have heard this name, PCM, DPCM, in all this modulation, you saw encoder is used, but not in every other modulation scheme the same encoder box can be utilized. So digital modulation is lower in complexity, and also digital modulation schemes are faster and easier to encode. So that's why we convert the analog to digital conversion, and then after that we again convert the analog digital to analog in order to get the output. So yeah, moving ahead, this conversion is called first step we should get is as a sampling. The sampling is nothing you can observe like a switch, like it's a switch which gets on or off. So if you have this continuous signals, then if you pass it through a switch, then you will get these signals with this part, only these values, or you can say these. Now you have to determine how many samples you should get, the minimum number of samples, so that the same number of samples can be utilized to get the same signal for that. So it is desired to calculate the minimum number of samples required for the reconstruction of the original symbols. So for that, what should be the sampling frequency? And according to the Nyquist criteria, the sampling frequency should be equals to 2 FM, should be less than or equals to 2 FM, should be greater than or equals to 2 FM. Yeah. So here it is required, because if you sampled it with lesser frequency, then you will not be able to construct the original signal. So this is the overall perspective of sampling. Then after that, using these samples, we we encode it and do analog to digital conversion. Sorry. Then we have, after that we do analog to digital conversion. Then after that we encode it. Then we quantize it, and then we will get a digital signal, digital amplifier, because amplitude gets low. So after this sampling, this analog to digital converter box is required, then encoder is required, and quantizer is required, then a digital amplifier is required. So in this particular course, we don't talk about digital communication. In next communication, which is the principle of communication system 2, you will see the digital communication in a depth. So this is all about the sampling. Now there are various types of sampling. First one is the impulse sampling, and second one is the pulse sampling, and third one is the natural what are the types of sampling you have studied in this?
Ma'am, that pulse sampling, flat top sampling,
And
and impulse sampling in the starting.
yeah.
And actually, ma'am, I also did from my side this one band pass signal sampling of.
Have you heard about this? Have you know about band pass sampling? I asked you to see, I think, yeah, it was the
Yes,
first.
ma'am. I tried it,
Uh,
and here we can get back the signal even if this sampling frequency is lesser than this Nyquist rate,
yes. Hmm.
because we have sample signal. They have a spectral gaps here, and the sampling frequency is equal to twice of this maximum frequency divided by some integer m, and this integer m is also having some relation with this maximum frequency and bandwidth of the band pass signal.
Yeah, yeah, yeah. So band pass sampling is different from this normal sampling because in band pass sampling, here it is not required fs to be greater than or equals to 2 fm.
Yes, ma'am.
Yeah, here we can also reconstruct the signal using fs somewhat less than or equals to 2 fm. So here there is lot of derivation in this, so that's why I have given the homework into that band pass sampling. But it is very important and one question you can definitely expect from gate perspective. So in this course, sir has not taught, I think, and nobody teaches actually. But in this what was the course? What was the book name? What was the book name? What book you refer here? Communication.
Ma'am, I used internet. There was one site. It had very
Good help.
elucidate.
Okay, nice. But yeah, the book which I referred, BP Lathi, sorry. BP Lathi is
BP.
also has also covered very depth, and in fact, I personally like this book very much because BP Lathi book is very good. I have read this book, so you can also go through it. So let us talk about this now. So the sampling frequency, which is Fs, and it is equals to 1 by Ts. And since it is a periodic process, the sampling frequency is the fundamental quantity of the sampling process. So the sampling frequency you can get, the sampling time period you can get is 1 by Fs. Ts equals to 1 by Fs. So what is the basic steps for getting sampling? The first one, you are multiplying the signal in time domain with the impulse train. So you are multiplying impulse train. Now this impulse train is in time domain. So in time domain, you have to write its Fourier trans Fourier trans sorry what is that, Fourier series. You will get
Yes,
some
ma'am.
Fourier series. Now if you multiply the Fourier series of impulse train, I have already derived this, that's why I'm not deriving, but I am just reminding you. You will get this shifted impulse. You will get. So here in time domain, if it is a multiplication, in the frequency domain, it will be the convolution. So xf into Fourier series of impulse train, and now you will get simply the xf minus f naught 1 by ts summation of nfs. Here f naught I am telling, nfs, n equals to minus infinity to infinity. So here you will get the sampled signal in frequency domain of sampled signal. And from that we observe also that fs should be greater than equals to 2 fm because of the guard time. Now in this lecture, sir has taught on another extra thing. What was that? Which is the reconstruction part as well. So how the sir is reconstructing the signal? Kushi, do you know?
Yes, ma'am. Just one second.
Yeah.
I have to refer my notes here. Sampling and reconstruction. Okay, first we were passing it through low pass filter with cutoff frequency centered around sampling frequency and magnitude, TS magnitude to cancel that 1 by TS factor.
Yeah, yeah, yeah. So again, what we are doing, we are again convolving with a filter. Like whatever we used to do in demodulation. What we used to do in demodulation we always used to have a low pass filter, right? Because we want
Yes, ma'am.
at the this message signal at the which was the baseband signal. Then again we have to reconstruct it. So this is one of the
Yes,
very
ma'am.
good filter, and the filter you observe that the filter is in the form of sync function.
Yes, ma'am.
So that is very important. So you have to remember this formula and the process as well. So here we will go through one by one. So we will see that here, as I taught, as I said, this one is the impulse train, and then the sample signal is this message signal into multiplication with the impulse train. Then this is impulse train, and now you are writing this in the form of Fourier series. So sample signal is this one. How will you write this term in term of Fourier series? Sir is doing so here sir is just multiplying with that. Okay, then we can follow also this. So here sir is multiplying this one. So after multiplication, this mt del t minus nts, it should be there because it is a different function. Now how you can write this one? This one you can write, that any multiplication of message, any multiplication of signal with the shifted version of delta function, you will get the message signal at that frequency or time with it. So here mt minus del t minus t naught is equals to mt naught del t minus t naught, this. So here you will get this, and here you are getting sample message signal. So here, if you if you if you if you just make Fourier transform here, so what is the Fourier transform? So you should know the time domain version of sample message signal. Here it is. Now, so so how will the spectrum look like? You have to see how will the spectrum look like. So MT, if you take it as a Fourier transform, so MF. Then how to fix the sampling parameters to minimize the distortion. So, Kushis, sir has not taken Fourier series or what? Sir has taken, right?
No, ma'am, sir also followed that same pattern.
Okay, okay.
Here,
Sir just make the spectrum in first picture. Then yeah, here the Fourier series sir has taken. Then in Fourier series, you know that we have to calculate CK. So the periodic coefficient CK is 1 by T, integration over one time period, which is minus Ts by 2 to Ts by 2 GST e power minus j 2 pi k fst dt. Now CK you got it as 1 by Ts. Yeah, 1 by Ts. I also calculated as 1 by Ts. So then 1 by Ts. And now how the Fourier series of the impulse train will look like? Here it will look like this. Now you know that this one is the coefficient for shifted in the frequency domain. So you will get the shifted frequency domain Fourier transform of impulse train. Here you will get the impulse train of this one. Then if you multiply this GSF with the normal MF, then you will get the shifted version of the your MF. So now you have to multiply with the MF. So I think sir has multiplied with MF, and here the multiplication in time domain will go as
convolution in frequency
yeah,
domain.
yeah. So here you will get this one, and the same formulation we also got here. So this is Fs or 1 by Ts, k is equals to minus infinity to infinity, m f minus kfs. So Kushit, you never forget this because this is very important. And
Yeah.
sometimes in interviews they directly ask the derivation of sampling theorem. So this is all about the derivation of sampling theorem. So if they ask derivation of sampling theorem for pulse sampling, so how will you calculate the pulse sampling? You know that pulse train you have to multiply with respect to pulse train. So pulse train can also be written as a Fourier series of sine and cosine, right? So you have
Yes.
to write the Fourier series of pulse function in sine and cosine. Then you have to convolve it with respect to xt. How will you convolve with xt? It is very difficult to convolve with xt and sine. So how will you do? You will just take the Fourier transform of sine and cosine. It's just the impulse. in in frequency domain. So convolution with impulse in frequency domain and simple MF, it will again lead to simply the shifted
Okay,
distance
ma'am.
in time domain.
Excuse me, ma'am.
Yeah, yeah.
What I did for pulse sampling, I practiced it little bit. So here my Fourier series coefficient was coming out in the form of sinc function, right?
Okay.
Uh, and then I was
How it
simply
is
multi.
coming in form of sync function? Because 1 by Ts rule.
Yes, ma'am. Yes, ma'am. I was taking it pulse of some duration, let us say tau duration pulse, and
Mm-hmm.
it was centered around origin. Yes, ma'am. No, ma'am. It was centered around origin here. That's why it became easy for me to calculate this CK.
Here
Otherwise, I
only.
had to. Yes, ma'am. Yes, ma'am. Yes, ma'am. So, Fourier series coefficient I calculated for one time period, and it came out to be sinc function. Um,
Yeah.
um,
Kushik, you
yes,
took
ma'am.
as a pulse train, right? Pulse train
Yes, ma'am.
only.
Yes, ma'am.
Okay,
Yes, ma'am.
okay. Then only you are just doing Fourier series. You remember this is a
And
pulse train.
then actually it was my Fourier series of this sampled signal. I'm sorry, Fourier transform of the sampled signal was in the form of this CK multiplied by the shifted version of
One
MF.
second, 1 second. Okay, you
Yes.
are getting this as in the form of sync. I'm just checking whether you have got
Yes.
proper answer or not. So, yeah, when I was also doing this, I also did this pulse sampling by myself.
So
So,
this Fourier transform
no,
will
no,
be
just
this
tell me
CK.
first
And
what the
yes, ma'am.
expression you are getting for. Do you have your notebook now here?
Yes, ma'am. What is expression for this CK?
No, no, yeah,
Okay.
CK is somewhat complicated, right? What is that?
Yes, ma'am. Please write down. It is FST1. First
FS.
FST. No, ma'am. First write down
Okay,
FST1,
okay.
then the sync of KFST1. FS is sampling frequency. T1 is my duration of this pulse. Sync of K times FST.
Hmm.
FST1. Sorry, K time FST1. Sync of K time FST1.
Okay, 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 okay. So generally, you have to, this is the Fourier coefficient for the pulse signal, and in every pulse signal, whether this one
Yes.
is the form of this one, or this one, you will get this one type of only. CK is equals to FST1.
Then there will be e to the power something should be multiplied for this shifting we are doing here
No, no, no.
in this
This term, I think this term will be different, because here it is what you are considering. Here you are considering as a
Okay, ma'am.
odd function. Even
Okay,
function.
ma'am.
This one is even function.
Yes, ma'am.
This
But
term,
if we actually shift it by half of its duration, then we are getting that same pulse here also. If we are shifting it by, if we shift this, yes, ma'am. So that's why I was saying that we will simply multiply it by e to the power minus that shifted portion.
okay, okay, okay. Okay, CK you got. Fine, fine. Yeah,
Yes, ma'am.
this term only
So
we got
it's
different. Uh-huh.
yes, ma'am. Its Fourier transform will be this CK and the impulses, right? Because it will be simply impulse shifted at this periodicity.
So what your question you're getting?
Ma'am, simply CK times delta of T minus N capital T, whatever is the duration of this pulse.
Okay,
Shifted impulse.
no, no, no.
Shifted.
This
Yes,
is
ma'am.
the CK, right? So you will write the Fourier series of pulse train.
Yes, yes, ma'am. And then I'm saying about Fourier transform. That will be
So
also CK
CK,
times
it is CK e
e
power
to the power j 2 pi k f.
FST,
Yes, ma'am.
okay? And
Yes,
here
ma'am.
it is just a shifted version you are saying. Okay.
Yes, ma'am.
Summation as well. CK this one. So
Yes, ma'am.
FS T1
And this will be multiplied by the message signal, our whatever signal we intend to sample in the time domain, and the frequency domain it will be convolution. So it will be again shifted spectrum of that sample signal.
Okay, so here we are not getting as a constant CK. Like in
No,
impulse
ma'am.
sampling, we were getting as 1 by Ts. So here it is a function of K
Yes,
and
ma'am.
T1. So you have to make sure
Duration
this is not
also.
function. And the final expression, what can you tell me the spectra of final
Yes, ma'am.
final?
Spectra is summation minus infinity to plus infinity
Yeah, K.
by ck times
Hmm.
x of f minus k times fs.
Okay, yeah.
X is our
F
signal being
minus.
sampled. F minus k times fs.
Yeah, yeah, yeah. This was what you used to get. But yeah, here you
Yes,
will get the impulse term. CK in CK you will get the
yes,
impulse
ma'am.
term.
From convolution from
Okay, okay,
after
okay.
this
Final,
convolution
final.
I'm
This one
getting.
is the
Yes,
final
ma'am.
expression.
Yes, ma'am. Yes.
Okay, okay. No, no, no.
And
I am
here
telling
also.
how will you draw this.
Yes, ma'am. Okay, ma'am. Okay, ma'am. Please continue.
So yeah. So impulse, the sync function will look like this one. Okay, and then mf minus fk. Here it will look like this. So final will be, here you will get the full magnitude, but here you will get a little bit magnitude, here you will get little bit magnitude, here you will get little bit and little bit. So in pulse sampling, what you're getting a varying magnitude at the output. So this was my motto, because in general we don't take, so in practice we have to take the filter, right? Filter you have to take. So filter
Ma'am,
means,
actually,
yeah.
excuse me, ma'am, it will be more complex than that because this CK is also varying sync function.
Yeah, yeah, varying
With
sync function we can say, but yeah, somewhat it will look like this only.
okay,
Somewhat
ma'am.
it is different, but you can, if you having doubt in graph plotter or not, so you can use the online graph plotter. You can just
Okay, ma'am.
put your expression and see what is the output. So I have put
Okay,
it in my time, so I was getting somewhat this, and why the reason is this, because in practice what is happening, due to long distance, we in after some time the signal strength decreases, so we don't require the same magnitude to be sent at all frequency, so we require this one only. So
yes, ma'am.
so at the end, you have ever heard the raised cosine pulse? So in raised cosine pulse you use sync function. So we don't use this normal pulse, but we use the raised cosine pulse, because after some time the magnitude decreases, and we also we know that this is only the required information, and at the receiver we only require this. So this one is all useless for us. So this is the main use of pulse sampling, and again the flat top sampling comes into the picture. So flat top sampling is required just by the pictorial version. For example, this one is this message signal, and this one is the flat top. So at the receiver, you require somewhat to look like this. If you get, you will get this one, this one, here, here, this one. But somewhat at the receiver, you don't require some varying magnitude at particular time interval. Suppose the pulse time interval. So you want this one to be flat. This
Here,
edges.
ma'am, noise can be easily removed if it affects the amplitude, right?
Yes, yes, yes. Yeah. And you know that noise is directly proportional to amplitude. It is not proportional to frequency. So that's why
Yes, ma'am.
we use frequency modulation for some other purpose and voice modulation from some other purpose. You know that SSB used for voice modulation, right? And VSB is
Yes, ma'am.
used for video modulation, while FM is used for,
FM is used for this radio broadcast.
yeah, FM radio. Yes, because
Yes,
these
ma'am.
are all required for long distance. So
Yes, ma'am.
noise will not be added and you will not be affected much. So yeah,
Okay, ma'am.
yeah, yeah.
Madam, here I don't see what is the difference between pulse modulation and flat top. Actually, I see similar, right? Here also there are pulses.
Yes, yes, yes. So here you are in flat. Here it is a flat top, because at the output you are getting as a flat top. But here in only pulse modulation you will get like this. He like this. That follows this wave curve. because simple multiplication of this one, right? But yeah, you are saying how you will get this. So after this, we pass it to some filters to get this flat top at the receiver.
Okay. Okay.
Yeah, only difference is this one. But why the scientists invented more? Because we require this flat to be considered. Uh, for example, the impulse sampling was first discovered. Then after that, pulse sampling discovered because we require this. Then again, the flat top sampling discovered because we require this for some purpose like noise removal and easy broadcasting. These are the purpose.
Okay.
Yeah. Okay. So this is what is about the sampling theorem. Then how will you how will you get the after this message signal that you have sent? So let us see this. So the same things which I taught in the class, Fs minus Fm, Fs should be less than. Now aliasing, yeah. So aliasing term is what the term aliasing means. Question?
Ma'am, distortion because of overlapping of the shifted waveform of that sample signal.
Okay. So since we know that sampling theorem should be less than or equals to maximum, sorry, greater than equals to 2 of
Greater.
Fm, right? Because it will lead
Yes.
to real aliasing. So distortion means what you're saying, like it is oversampling or undersampling.
It is undersampling, not oversampling.
Okay.
Undersampling.
So what is called under oversampling?
Ma'am, when it sampling rate is much greater than two times the maximum frequency, then there will be spectral gaps between those shifted
Yes,
version.
yes, and now you know that in spectrum is very limited, so you
Yes.
don't require to waste. You
Too
don't
much
need to
spectrum.
waste much frequency for that. So you don't have that much frequency as well. You know this the millimeter wave is coming. In fact, it has come. So what is the frequency of millimeter wave?
I don't know, ma'am.
Okay, no issue. So some practical knowledge, if we like the PM Modi has launched 5G, right? So it was
Yes, ma'am.
all our part, like it is all from the electronics and communication part. So yeah,
Okay.
the 5G has come. So it has two frequency, FR1 or FR2. Frequency one is up to 39 gigahertz. After 39 gigahertz, it is FR2. So here it is called millimeter wave. Why millimeter wave? Because if you take the lambda of this, you will get in the form of millimeter, order of millimeter.
Okay, ma'am.
Since it is a order of millimeter, so it will cover very less distance, very less distance. So for that, you will have frequency reuse concept come. So yeah, so these are the actual frequency going now. For 5G, we have up to 39 gigahertz and for greater than also 39 gigahertz. And in 6G, mostly more frequency will be absorbed. So in the news also they were saying that radiation is causing some issues. But yeah, these are in the you should know this is the in the order of millimeter wave. But what is the what is the wavelength of the visible light? It is the wavelength of visible light is a nanometer range. It can't even reach the nanometer to the millimeter. Millimeter is far way beyond for the nanometer. So all the bullshit was wrong. Like 5G is not at all doing anything with the us. It is not doing anything with the. It is
Okay.
not. Yeah, yeah,
Ma'am, a very silly question actually.
yeah, yeah.
Like I understood this concept of millimeter wave, why it is called, so it covers less distance. But can you please explain a little bit how it is related to this frequency reuse concept?
Yeah, yeah, yeah. So,
Not getting.
mhm. So for example, if it is covering a hexagonal pattern, the area is covering a hexagonal pattern, right? So if it is F1 and if it is F2 and if it is F3, I'm telling F1, F2, F3 as a base station. So for example, the base station is having this frequency and the base station is having this frequency. And again this distance come and again this distance come. I have covered all the coverage area into a hexagonal patterns.
Okay, ma'am.
Yeah. So for example, if it is a user of this one, this user, since it is covering only this much distance, so we have to use for another user is going from this cell to this cell. Then handover comes. Handover, handover. You must have heard about it. Then handover comes. For example, again this user comes to this frequent this cell, then again we have to use only this frequency because it only covers only less distance, so you're having only small cells
Okay.
because less distance
Got
means
it, ma'am.
small. So again you have
Means
to
the
use only this.
distance this will cover is limited, and so in the frequency reducing concept.
Yeah,
Okay.
this is very common. So
Yeah.
and
Also, madam,
yeah.
because of millimeter waves, we have to use more cells, right? More cells in
Yeah,
the same.
true. Yeah, because
Okay.
we are, since the demand is increasing, more users you have, mobility is also increasing, you have more vehicles you have. So my research area is also on the V2X technology. V2X means the vehicles communication, how the vehicles are communicating with each other. So, users, I'm considering the vehicle as one of the users. So millimeter waves cells is more. Yes, sir. Continue.
Yeah. Okay.
Yeah. So Deepika, you have joined now, so no issue. So we have talked about the sampling theorem, the construction of the sampling theorem, and why it is needed. So let us talk a little bit about the this reconstruction of original signal from the samples, of which is it is also called sync interpolation. So sometimes you get confused, but yeah, it is a sync interpolation. So let us see. So the sampling and reconstruction, you saw this ms is equals to mt into this multiplication of the impulse train. Then after multiplication, this is the impulse train which fs is equals to 1 by ts. Then you are getting this term is in the time domain as this one. Then after this, you are getting this final spectra, Fourier transform spectra of the sample function, which is m del f. This is why del, because it is a impulse sampling. Now how will you reconstruct it? So some of the spectral copies, or the sir has written in this way. So this is the overlap. Overlap leads to distortion, which is the aliasing. Again, we have covered where sir has taught. I think so. Yeah, you know this is a spectra we are getting at the receiver. Now you have to pass it to a low pass filter. So this low pass filter, we have to pass it to a low pass filter. And now this low pass filter should have this frequency of fs by 2 to minus fs by 2. Why it is? Why it is? Because here fm fs minus fm is greater than fm, and here minus fs plus fm should be greater than minus fs by 2. So here you should have at least fs by 2 to fs by 2. Why it is fs by 2 to fs by 2? Why the filter is only from fs by 2 to fs by 2?
Ma'am, it is satisfying that Nyquist criteria, right? So from there it comes, no? Fs by 2 minus Fs.
Yeah. So fm, this is fs by 2, because here fs should be greater than equals to
Filter
2
should
fs
be
by 2.
less than equal to minus Fs by 2, so that other samples don't intervene here.
Yeah, it should be there. It should be there, fm. So fm should be less than equals to fs by 2. Or you can see from this one also. This
Madam,
also it is, yeah.
madam, because that is a baseband signal, so it is not shifted. So Fs should be okay. Minus Fs by 2 plus Fs by 2. Uh,
Which is not shifted.
because that we call as a baseband, right? Minus
Yeah,
Fs by 2.
yeah. So we want this signal at the output. So what should be the cutoff frequency for the filter? I'm asking. So it is only fs by 2. I'm not. I didn't get what you're saying about not shifted thing.
Okay. Okay. So what you are saying is the low pass filter. the frequency range is minus fs by 2 to plus fs by 2, right?
Yeah, yeah, yeah.
Yeah.
Why
Okay.
it is that? Due to sampling theorem itself, we get it. Otherwise, it will lead to the aliasing effect. Yeah,
Yes, because fs is the highest. Fs is greater than 2 fm, so that is
yeah.
the that
Otherwise,
accommodates
yes,
message inside. Yes, message frequency.
yeah. So otherwise, it will lead to aliasing effect. Then, hello, hello. One second, my mic is working fine or not. Hello, hello. Yeah. So yeah, then by using a low pass filter with a cutoff frequency of fs by 2, so whenever however the filter is from minus fs by 2 to plus fs by 2, but whenever the bandwidth is asked, so what should be the bandwidth? The bandwidth is only fs by 2 because we only consider the positive frequency in the bandwidth part. So you have to remember that the negative frequency has no effect on bandwidth. So yeah,
Madam, can you explain that statement?
yeah,
Negative
yeah, yeah.
frequency has no effect on bandwidth, because I always thought bandwidth is minus fs by 2, 2 to plus fs by 2. Okay, so it is fs. So you are saying
Okay,
bandwidth is
okay.
fs by 2. I
Yes,
thought it
yes.
bandwidth is fs.
Uh-huh. Okay. So, sir, in practice, since the negative frequency concept came from the use of complex variables and all, it's like graphically you can see. But in bandwidth calculation, whenever anybody ask, or in practice also, the positive frequency is considered. For easier understanding, like this frequency even doesn't exist, like in message signal, does it exist in practice? This negative part, this doesn't exist in negative part. So we are only getting this one in practice. So we are using the cutoff frequency as fs by 2, so the bandwidth is fs by 2 only. Bandwidth is fs by 2 because in bandwidth we only consider positive part, we don't consider negative part, because in
Okay.
practice also this part doesn't exist, only this part exists.
Okay. Okay. That means the low pass filter cutoff frequency is fs by 2.
Yeah, yeah, yeah. And cutoff frequency here, sometimes also called as low pass filter with bandwidth as fs by 2. It can also be referred as this.
Okay. Okay.
Yeah.
But your concept will change if it is a high pass filter, right?
Yeah, it will change because in high pass filter, yes, yes, positive frequency. That's why I'm saying I always consider positive frequency for the bandwidth calculation.
So for high pass filter, it is both. It is double, right?
No, no, no. It will
Hmm.
be somewhat fs plus fc.
FM, yeah, FS
Fs.
minus.
So what is the difference? Here it will be fc. The bandwidth is fc.
Okay, okay, okay.
So let me tell you one thing. The definition of bandwidth. The bandwidth is the range of positive frequency for which the amplitude is constant. So you have to think the for which the amplitude is constant. So for example, if you have this signal, this signal, this signal. So this is the range of frequency fc0. The range of frequency for which the amplitude is constant. The amplitude must be considered for you are considering the bandwidth.
Okay.
So yeah. So this is the bandwidth. Then what should be the HF? Uh, since you are having this one minus fs by 2 to fs by 2, then you are taking as a ts. Why ts? Because in here you are getting is 1 by ts. So 1 by ts multiplied with ts, you will get simple 1. So this is what you required. So we take hf is equals to ts if a mod of f is less than or equals to fs by 2 and 0 otherwise. So let me take my mic like this. Yeah. So, what should be the time domain of this HF? So, how will you calculate this? So, you're getting sync FST, where sync FXT is sync pi FST or pi FST. So, let me revise one thing. tau by 2 minus tau by 2. Fourier transform, duality, here somewhat, here negative of this. Okay. So tell me, what is the expression? Here F, frequency domain.
Ma'am, that frequency transform of that upper
Yes,
function will be
mm,
a times tau times sinc of f tau.
nice, nice,
F.
nice. Yeah,
Yes, ma'am.
so this is one is A tau sync F tau. Why? Because I told you this trick. This one is area, this one is pulse width. This one
Yes,
is
ma'am.
pulse width. What is the area? Area is A into pulse width. So A tau sync F tau. Remember this. If you remember this, you don't have any problem with calculation of sync tau and any function. For example, if you even asked to calculate this function, you can calculate without any issue.
Yes, ma'am.
So using duality, how you will get this part? So using duality, yeah, Kosha, tell me.
Okay, ma'am. Time domain function will be a tau sinc of t times tau,
Yeah,
and here it will be pulse of height a, duration tau. Yes, ma'am. Duration tau total means minus tau by
yeah,
2 to
yeah.
plus
So here
and
yes,
infinity.
since it is a
Yes, ma'am.
even function, you don't have any issue.
Yes, ma'am.
Otherwise, odd function, it will be negative of that.
Yes, ma'am.
Hmm. So one more thing. Do you remember this particular a
Hmm.
or tau? I can say yeah,
Yes, ma'am. Actually, we convolve that rectangular pulse with itself, then we will get
yeah,
this
yeah,
one.
yeah, yeah, yeah. So here is will a tau area sync square f tau. Here you have to remember this is the pulse width by 2. I remember like this. It is a pulse width, pulse not
Yes, ma'am.
triangle width by 2 by 2, or here it is area. And you have to remember this is a sync square.
Yes, ma'am.
And why I'm talking about this function sync square? Because the Fourier transform of sync square is also sync square. If it is in the
Fourier
time domain,
transform.
Fourier transform of sync square is also sync square.
Okay.
Yeah. So it is very important. Now, how will you write the HT? So you can write this. You can easily get, even in fact, we can write like this: TS FS by 2.
Ma'am, excuse me, ma'am.
Yeah, yeah,
Can I have one look at that triangular function?
yeah, sure.
Yes. Here it will be simply area A times tau if this is here tau and sinc a square F tau. Okay, ma'am, got it.
Yeah, yeah.
Got
You also, along with this, you also remember this. Yeah, this one
it.
and
Yes,
this one.
yes, ma'am.
So, where I was there, I think, this one.
Yes,
Ah.
yes, ma'am.
So, how you can write the Fourier transform of this one? Sorry, inverse Fourier transform, because here it is time frequency domain, and we are talking about time domain. So, HT will be, what is that? A area. What is the area? Area into Fs
Fs
into
times Ts times sinc of
Fs.
FST. FST. FST, ma'am.
Yeah, yeah. Let me see. FST. Yeah. Hmm. So, sir has not taken this amplitude part or what? Let me see. So, why he
Sinc
has
of FST.
battery? So, let me on the battery of the computer. Battery. Sir has not taken this amplitude. I'm just wondering. Yes, it should have.
Ma'am,
Okay, okay.
it
TSFS
will
is one.
cancel out. Yes, ma'am, it
TSFS is
will
one.
cancel.
Okay, okay. So yeah, so you always remember this formula. This is always correct. So I was verifying this formula with you. So TSFS is one. FST. Okay. Then sync FST. ST is sync FST. Okay. So this is the reconstruction filter. We all also call this. So for reconstruction, you have this MST, which is a sampled version of the of the message signal. Then you pass it to a reconstruction filter, which is HT, and ST is equals to sync FST, and you are getting as MT, which is the baseband signal which we passed it. Now you observe. Now sir has made draw the spectra of this. I think. Yeah, what MT we can write? So MT is MST, which is the convolution with the this one MST sampled version of this signal. Then this one is HT, and this one is MST convolved with, and you get convolution as this one, and final version you get MT is equals to this one. So how you can write MT? So using mathematics you can get it. Yeah, M0, MTS, M2TS. This is what the interpolation means. So interpolation means you are varying the time of message signal by some amount. So for example, here MT you are getting, but you are getting the interpolated T version. So what is the final expression you are getting? This is the final expression, which is MT is equals to NTS sync FST minus M. And so you are just shifting it and interpolating it, and after interpolation you will get, so after this you will get final MT. So how, this is
Ma'am, it
how.
is simply some sort of convolution we can say, or convolution is a special case of interpolation.
Yeah, true, true. Convolution is a special case of interpolation. Yes.
Yes, ma'am.
So we can see this. Now this is all about the frequency domain of, sorry, frequency modulation. So frequency modulation, I think the questions of the week six are mostly related to frequency modulation. So for that, I used it for your purpose. So what is the modulation index for FM? It is the delta F by FM, KF AM by FM. Okay, and the time domain equation of FM is AC cos 2 pi FCT, 2 pi FCT plus 2 pi KF integration of MT dt. And this is the time domain equation of FM. Time domain equation of FM. Now we saw this as instantaneous frequency deviation. So it also depends on the amplitude of the message signal. So it doesn't depend on frequency of the message signal itself. So you have to remember this. And what if we double the time period of the message signal? So if you know that modulation index is equals to delta F by FM. So beta when time if you double the frequency FM. So frequency multiplier, frequency multiplier, you know, this one is beta when it is giving, and you have beta as input. Then beta 1 is equals to delta F by FM1. Now delta F by 2 FM. So you know beta nu is directly proportional to beta 1 by 2, because it is all also depends on AM and FM. So if you are multiplying the frequency by 2, you are getting beta as a division by 2. To make beta unchanged, we have to increase the amplitude as well, because AM, if you change the AM as AM by 2, then you can unchange beta. So you have to remember beta also depends on amplitude as well as frequency. Which is a what is a beta? Beta is the modulation index of the frequency modulation. So types of FM you have heard: narrowband frequency modulation and the wideband frequency modulation. Narrowband, narrowband which is narrower. Why when it is narrower? When the beta is less than one, and wideband when beta is greater than one. So how the frequency spectra of the FM looks like? So here you will
Ma'am,
have, yeah.
ma'am, beta will be less than 1 or it will be much, much lesser than 1 for it to be considered as narrow band?
In general, beta is around
Because
0.5 to 2.
sir took these approximations like cos of theta is equal to 1 sin theta equal to theta. So that they will be valid only for much, much lesser than 1 values, I think.
Yes, much less. But theta, yeah, yeah. Here you are saying, no, beta
Yes,
is
ma'am, that's how we were getting this simpler expression in terms of beta, I see.
yeah, true, true. Here, beta should be much less than one. In practical example, if you are getting what should be the value, then if you have solved some questions or the questions has taken some value, right? So we can see from that also. But point
Okay.
one is also taken somewhere. I saw. So point one beta is usually point one. So point one is also very very less than one, right? Point one and one. So you can consider.
Okay.
Yeah. So the spectra looks like this. Why I'm taking, because here we will solve the questions related to this. And also, what is the bandwidth of this one? It is a 2 FM. And what is the bandwidth for AM?
Bandwidth for ma'am, it was sensitivity into that message signal magnitude of message signal.
No, 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 bandwidth of AM.
Okay, that was modulation index. Okay, bandwidth, ma'am.
Bandwidth is also,
Sorry.
it is, what was that? It is FC plus FM,
Okay, 2 FM.
FC minus FM, right? So 2 FM.
Yes.
So that here also we consider only positive frequency. KG Krishna sir, we are here also we are considering positive frequency. So
Yes, yes, yeah. This is where I thought.
so we only consider positive frequency. So bandwidth for FM and AM it is same. Okay.
Okay.
And in SSB, what is the bandwidth?
FM.
Yeah, and DSB?
VSB FM plus some vestigial amount.
Yeah, VSB. DSB.
DSB it was 2 FM only.
Hmm.
2 FM only.
Hmm. So in DSB you have 2 FM. In SSB you have FM. And so you remember these things, okay? Okay. Now it is for the narrow band, but bandwidth for FM using Carson's rule is 2 beta plus
Yes,
1
ma'am.
into FM, okay, because we are considering only Carson's rule. So the generation of narrow band FM, and then Bessel's function. And I must say, please refer this derivation, which is explained by Aditya sir. So this was my derivation. So I have referred. So at the end, you have beta plus 1 into FM. And in here, one more thing, the efficiency is always 100%. So in AM modulation, the efficiency was maximum 33%. So here the efficiency is always 100%. Why? Because in every component you only have frequency modulation component. If you see this AC beta by 4, then EC minus AC beta by 4, again then AC beta by 4. So you remember, sometimes the spectra is given to you some values, then you have to calculate the power levels and all. So you please try to cope up with it. So these was all the previous questions. Then we will solve these questions. So consider an AFM signal with the instantaneous frequency FIT is equals to FC plus KFAM cos 2 pi FMT. The modulation index beta of the FM signal is,
Ma'am, C option. KFM by FM.
yeah. So very nice. Modulation index is defined as del f
Delta F by FM.
fm, then kf am by fm. You please remember kf am. It also inversely proportional to fm. So one more thing, why we consider this one as message signal, this particular message signal, because whenever the frequency increases the amplitude decreases, whenever the frequency and vice versa. So we used to consider this thing. Okay, so the next question, the frequency modulated FM signal is described as XCT is equals to 10 cos 6 pi into 10 power 6 t plus 1 by 4 sine 800 pi t. The approximate bandwidth of XCT calculated using Carson's rule is XCT is the frequency modulation. So you have MT, you have FM, and you are getting XCT. Here you take XT. You have to identify what are the things you have to identify. Beta. For beta you have to identify del f. For del f you have to identify kf am and fm. So let us calculate what is kf.
KF each my one
You
second.
cannot calculate, right? Kf am is
No,
1 by 4.
beta we can calculate one by
Okay, yeah, beta
delta.
beta, sorry, yeah, beta is 1 by 4. Beta 10 cos 2 pi fct plus beta sin 2 pi fmt. Yeah, what is that? Xct can be written as AC cos 2 pi fct plus beta sine 2 pi fmt, right? And from
Yes,
that, we can calculate beta is equals to 1 by 4, fm is 400, and yeah. So using Carson's rule, bandwidth is equals to 2 beta plus 1 into fm. Now 2 1 by 4 plus 1 into fm, which is 400. So what is the final answer? 2 into 5 by 4 into 400. 100,000 is the answer. 1 kilohertz. Okay.
yes, ma'am. Yes,
1 kilohertz. Okay. So you remember this one, time domain equation. It is only for narrowband FM. Beta is less than
yes,
1. Here also narrowband should be mentioned. But yeah, it is not mentioned. No issue. Now let us solve this question. Consider a narrowband frequency modulated signal with modulation index beta is given as an input to frequency multiplier by factor of n. I took the example of frequency multiplier by factor of 2. Right? You are having here frequency multiplier by factor of n. So
yes,
frequency
ma'am.
multiplier factor is n. Tell me,
Ma'am, n times beta.
n times beta. How?
Yes, ma'am, its frequency will be multiplied by n times to n times suppose carrier frequency is fc to n times fc plus n times kf into m it will become. So that quantity is beta actually. So it becomes n times beta.
Are you sure?
Yes, ma'am. I am multiplying instantaneous frequency by n. Yes, ma'am.
So
Yes, ma'am. N times beta.
okay.
Ma'am, the message signals frequency will not be multiplied by n because message frequency is inside that message signal. The instantaneous frequency, the complete message signal, its amplitude is being multiplied by n. So that n will come in the upper numerator.
Okay. Nice. So yeah, this type of mathematics you should remember because you are remembering this one AC cos 2 pi
Yes,
fct
yes.
plus beta sine 2 pi fmt.
So FM will not be multiplied anyhow.
So frequency multiplier here is this one is the frequency. So the whole term will be multiplied by n multiplication. Nice. Answer is A. A frequency modulated FM signal with a carrier frequency FC is equals to 303 into 10 to the power 8 is just try with the equation this one, which is phi t is equals to 10 cos 2 pi fct plus 6 cos. You just see, like in every question you are saying narrow band FM, right? So in practice also we only see narrow band FM. We don't consider wide band FM as
Okay,
in
ma'am.
practice. So you find the frequency deviation, frequency maximum frequency deviation.
Okay, ma'am.
It is a maximum frequency deviation.
Ma'am, 6 kilohertz.
You're just okay. It is given as this one. How you are calculating 6 kilohertz?
Be- Beta is 6 and it is equal to delta F by FM. And FM is 1000. Yes, ma'am. FM is 1000.
Delta F by FM. Okay. So delta F is equals to 6 into FM.
FM is 2000 pi divided by 2 pi 1.
Okay, okay. 6000 by 2. Nice. So answer is 1. Hmm. Let us move to the fifth question. Consider an FM signal with a carrier frequency FC, a modulation index beta, and a message signal AM cos 2 pi FMT. The instantaneous frequency of the signal is.
Second one. Sorry, ma'am. Not second one. It will be. Yes, ma'am. Second one. Second option.
So just you have used the formula, right?
Yes, ma'am.
What is the formula? FC
Instantaneous frequency will be simply this plus.
STFM. So in every equation we are using only this one, cos 2
Yes,
pi
ma'am.
FCT plus beta sine 2
Plus
pi FMT.
signal will be beta. Yes, ma'am.
So what is the
No,
here?
ma'am. Instantaneous frequency will be FC plus some constant times this message signal, and that constant times multiplied by message signal amplitude is actually beta. So FC plus beta cos 2 pi.
So B C option, right?
No, ma'am. I will go with B option.
Why you are going with B option?
Ma'am, FM should not come in multiplication. FM will not come in
Answer is
multiplication.
no. Option is C. I think option is C. I
Ma'am,
think.
when we will write the phase, there we will integrate it or anything we will do with that. If we are writing instantaneous frequency, then there is nothing to integrate.
No. See,
Okay.
del F how you write? FC plus
Hmm.
KFAM. Suppose cos 2 pi FMT, right?
Ma'am, del F will be simply KFM cos 2 pi FMT. This
No.
is frequency decreasing.
Del F.
Okay, ma'am. Got it.
Yeah, del F is
Instantaneous.
FC cos 2 pi or FC plus KFAM cos 2 pi FMT. So
Okay.
according to this, it should be this one. FM should be coming. Did you get it?
Ma'am, where FM is coming? I didn't get it. Where FM is coming in the expression?
FM KFAM cos 2 pi FMT. So beta okay. No.
Okay, ma'am, got it. The answer will be
KFAM
then.
KFAM you
The
have to
answer
write.
will
No,
be then.
beta is
Yes,
equals to what is that? Yeah. Answer is C. I
delta
remember
F.
this answer. Answer is
Yes,
C.
ma'am.
KFAM by FM. Why this?
Beta equal to
Huh,
delta F by FM, and here,
KFAM
yes, ma'am.
beta. So KFAM.
Beta FM
Huh,
times equal to delta F. This is maximum frequency deviation actually.
yes.
That component. Okay,
So
ma'am.
frequency deviation.
Okay, ma'am. Got it.
Hmm. So answer is C. So sometimes you get confused. So what to
No,
do? Whatever you have. Yes.
madam, answer is C, right?
Yeah.
C.
C. Huh. So sometimes we get confused. You just go with the basic equation. You can try to cover with, for example, here we were having beta. So just think how we can write in terms of beta. So because we are not getting beta. So beta
Ma'am,
and FM. Yeah.
excuse me, ma'am.
Yeah.
Ma'am, in that second expression, I think you should write Fi because they will confuse here. Those who will see this video later on, they
Hmm.
will confuse this delta F with maximum frequency. Yes, ma'am. Now
Fi
it's okay.
is what? Fi is equals to del F plus.
Instantaneous, instantaneous frequency.
Uh,
Yes, ma'am. And this is
del
maximum frequency deviation.
instantaneous
Yes, ma'am.
frequency. Okay.
Yes,
Okay.
ma'am.
Thanks for correcting. Okay. So
It's okay.
let us go to sixth question. Consider the phase modulated signal. Yeah, here you are having phase modulation. So, question, can you tell me the difference between phase modulation and frequency modulation time domain equation? STPM.
Yes, ma'am. Phase modulated signal has simple, very simple equation like here it is given in the question.
Cos 2
And
pi
there
f.
we will have integration of the message signal when we write this frequency modulation.
Uh,
Integration of the message signal. Yes, ma'am.
okay.
I'm talking.
Huh. So, you please remember these two.
An
Now, let
answer
us.
will be
Yes.
here.
Modulation index. Yes, yes. So, here you can see the modulation index for the PM phase modulation is directly proportional to AM, but not depending on frequency or phase, anything. So,
Uh,
yeah.
Madam, here the method you're following is that phase modulation, you're converting it to frequency modulation by integral here, right?
Yes, 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 yes,
So
yes.
the above equation, AC cos 2 pi ft kp mt is actually the phase modulation because the phase is changing. I can see 2 pi ft plus. Okay, that you are expressing in terms of frequency modulation by integrating the phase.
Yes,
Huh?
after if you are having this phase model, for example, frequency modulation, if you pass this the differentiation of MT, you will get phase modulation. So
Okay.
you just suppose differentiate in term d by dt. But here you should remember Kp is equals to 2 pi kf.
Sir, may I speak, ma'am?
Yeah, yeah.
Okay.
Mm.
Sir, when you integrate this frequency, you get the phase, and when you differentiate the phase, you get the frequency. Both are related, actually.
Oh, okay, okay.
So here the MT along with this Kp Am cos 2 pi FMT. So this is called the beta for phase modulation. So yeah, moving to the next question. Consider it is simple. What is that? It's just saying consider an FM signal with the frequency deviation del f and a modulation index beta. The approximate bandwidth of the signal from Carson's rule is given as, what is that?
And B1, B option.
Okay, 2 beta plus 1 into FM. Now beta is written as,
No, ma'am, not first one, second one, second one.
okay, 2 1 plus 1 by beta into del f. How you are saying this one? 2 beta plus 1 into beta del f.
Then simply write beta as delta F by Fm, and we will get 2 times delta F plus 2 times Fm.
Yeah, delta f, sorry, this one delta f. So 2 beta plus 1 into fm. So any form is fine. This one is the answer is B. Now, yeah, question number 9. Consider a
Yes, miss.
parallel resonant LC circuit with L is equals to this one and capacitance of the variable capacitance is this one. Now you have to calculate the carrier frequency of the resulting frequency modulated signal. So here it is the oscillator. So oscillator frequency you know from the analog circuits, right? What is that? 1 over
1 by
f.
root under LC,
1 under
omega
LC.
h.
So it is f. So
Yes,
you
ma'am.
have to calculate the value. What is the value? Please calculate. Yeah, take your time. Please calculate.
LC. Ma'am, approximately 1 kilohertz I am getting. 1.00658.
One, okay, what you are getting? 1.0. Okay, so
1.00658
answer
kilohertz for
is
1 kilo.
around 1 kilohertz, right? Nice.
Yes, ma'am.
So answer is D. So anytime the oscillator comes, then it is one this type of frequency is this, because this one is a resonance frequency. Okay. Moving to the ninth question. A frequency modulated FM signal is described as XCT is equals to 20 cos 4 pi 10 power 70 2 plus 2 sine this one. The approximate bandwidth using constant intervals. So similar bandwidth is 2 beta plus 1 into FM, 2 plus 1 into FM, 2 into FM2,
Ma'am, 3 kilohertz.
9, no? Getting 9
3.
kilohertz.
I'm getting 3 kilohertz, ma'am. I'm getting 3 kilohertz.
So
3
see
times.
my solution where it is wrong.
Okay, ma'am. Ma'am, it is
9 only
1
getting.
plus 1. No, ma'am, it is 1 plus 1 by beta. The formula is wrong in the first line.
No, beta plus 1
1
into
plus.
FM, na? Beta is 2. Beta
Okay,
is
one
2.
second. One second, ma'am. It is 2 into. Ma'am, 2 into 1 plus 1 by beta into delta F.
No, no,
O-
no.
Okay, okay,
It is
one,
beta
one,
plus 1 into FM.
one into FM.
Answer is C only. Yeah.
Okay,
So
ma'am.
beta, you know this AC cos 2 pi FCT, 2 pi FCT plus beta sine 2 pi FMT. Beta is 2. The bandwidth is 2 into beta plus 1 into FM. Here
Okay,
I am
just
taking.
one second, ma'am.
Yeah, yeah,
Ma'am,
sure.
just
Hmm.
one second. Plus. Okay, 2 into beta plus delta. Okay, ma'am, I was wrong. Yes,
Okay.
ma'am.
So answer is 9 kilohertz. So see, sometimes we know you know the formula and you know everything, but sometimes in calculation we get mistakes. So please try to solve in a proper rough, so that whenever you come back and you can see for your competitive exams. Okay.
Yes, ma'am.
So question number 10. This one is very good question. I want you to first try. Then if I'm not able to solve, then we will solve.
Maximum frequency 50
So I'll
hertz.
read this question. A given phase modulated signal has a frequency deviation of 50 hertz for an input sinusoid of unit amplitude and frequency of 120 hertz. Determine the required frequency multiplication factor to produce a maximum frequency deviation of 20 kilohertz when the input sinusoid has a unit amplitude and a frequency of 240 hertz.
Ma'am, 200.
Yeah, the answer is correct. 200. You have calculated.
Ma'am, in the first case, beta equal to delta F by FM, it is 50 by 120. In the second case, beta equal to 20,000 by 240. And
50 by 120
yes, ma'am.
by
In the second case, it is
PM, right?
20,000 by 2. Yes, ma'am.
In the first case, you are saying PM or FM?
Ma'am, FM, delta F by FM,
Yeah, yeah,
FM.
that's why. Here, KF means
And
no.
second case, it is second case, it is 20,000 by 240. It is in kilohertz in the second case.
20,000, 20 kilohertz,
By
right? 20 kilohertz
yes,
by
by
2.
240.
Hmm.
And n times first beta equal to this second beta, and we are getting 200.
N times the first beta. Okay. Beta 1, beta 2. So beta 2 is equals to N times beta 1. Okay. So, okay, you have taken this approach. This is fine. So I will tell my approach. So del F is 50, which is kp am FM, and KP AM. What is AM? AM is 1, FM is 120, which implies KP is equals to 50 by 120. KP AM. Yeah. So which implies 50 is equals to, and multiplication factor अगर n है, then the resulting frequency deviation in 1 to 40 hertz is n, simply multiplication of n kp am fm, and if you put this value using this you will get 200. Question number, yeah, and this approach is fine, nice. So this was all about this question of week 6, and I think half an hour still left, but we can leave, no issue. But yeah, this was the week 6, and in week 6, I taught this one, analogs to digital conversion of signals and introduction to sampling. So I think up to week 6, we have covered, we have completed all this half of the course. So a far more to go. So with this, I think we should leave. Thank you.
Okay, ma'am. Thank you very much.
Thank you.
Thank you, Amara.